Those of you who are long-term FiRe people have seen Lee once here before. It is his second time giving us an opening night speech. He has done many things since then. He is a good friend and a great scientist. He inspires us all who know him on a regular basis. That's before we learn that he does 100 push-ups a night. And he has done a lot of things in his life which are amazing. The factoid that I always kind of first stumble upon is, if you like the idea of a genome, thank Lee. He invented 4 machines which made all of that possible. It's hard to believe that one person would be involved in all 4 machines and that one person would lead to everything we know about genetics. It's an incredible thing, and we thank you, Lee, for doing that. I won't, you've got his bio yourselves. I'll just mention a few things which I think are particularly standout things. Among them, he's played a role in founding 15 biotech companies, including Amgen, not bad, Applied Biosystems, Integrated Diagnostics, and Aravail, which is a new company, very exciting company in Seattle. He's a member of the National Academy of Sciences, the National Academy of Engineering, and the Institute of Medicine. Of the more than 6,000 scientists worldwide who belong to one or more of these academies, Lee is only one of 15 people nominated to all 3. He's authored a number of books. He's working on a book now. One of his better-known books is The Code of Codes, and he's about to produce a text on systems biology, which is his specialty. He's received many national and international awards, including the Lasker Award for Studies of Immune Diversity, the Kyoto Prize, these are all amazing prizes, in Advanced Technology, the Heinz Award for Pioneering Work in Systems Biology, and the coveted NAE 2011 Fritz J. and Dolores H. Russ Prize for developing automated DNA sequencing. In addition to having received 17 honorary degrees from prestigious universities in the U.S. and abroad, Lee has published over 750 peer-reviewed articles and currently holds 36 patents. In 2013, he received the National Medal of Science from President Obama. He has been named by the best schools as one of the 50 most influential scientists in the world today, and Scientific American has named him as one of the top 6 in their selection of 100 biotech visionaries worldwide. Please give a big hand to Lee Hood.
Well, thank you, Mark. What I'd like to do tonight is convince you that the title I've given you here is bold, but we're moving in the right direction to make it actually become true. And to begin with, you have to understand that in the last 100 years or so, there have been 2 revolutionary events in medicine that have really fundamentally changed medicine in an interesting way. And the first of these events was a report that was filed in 1910 by the Carnegie Institute that surveyed 155 trade medical schools and came to the conclusion that they were unmitigated disasters. And in fact, what the report recommended is, 1, that they apply science to healthcare, and 2, that they apply science to the education of medical students. And a few institutions really hopped on this bandwagon. One was Hopkins, and it really led the way. And it shows you, if you have the courage to participate at the leading edge of paradigm changes, you can really transform medicine and establish yourself, as Hopkins did, as a leader, and that leadership continues today. And I call that 20th century medicine. And to be more explicit about what 20th century medicine is, it's listed here. These are the classic topics in the last century that medical students learned, the focus was entirely on disease, and it was all about how you fix disease. So what exactly is 21st century medicine? It's what I'm going to talk about today. It's taking a systems approach to disease and to healthcare, and that fundamentally changes how we think about things. It's using high technology, high throughput methodologies. It's using the digital devices. It's making measurements of many different features in your body. We'll talk about that in some detail. And in 21st century medicine, it's all about prediction, prevention, and personalized medicine. The medicine of the 21st century is about the medicine of the individual. It's not about medicine of averaged populations, and I'm really going to make that point very forcefully. Actually, if you want to read a terrific book, read The End of Average by Todd Rose, a Harvard professor, who talks about how averages have misled us in every dimension of life, and especially in science and in medicine. So the 21st century medicine is about understanding wellness, about understanding disease, and most important of all, as you'll come to appreciate, understanding the transitions between these two states. Because if you attack disease at the transition and can reverse it, then you can lead to an end of disease. That's the essence of the message I'm going to deliver tonight. So what does 21st century medicine allow us to think about doing? One, the quality of American healthcare is really abysmal today, and I'm going to say more about that later. We fall in the lowest quintile of the top 20 developed countries, in spite of the fact we spend 5 times or more as much as any one of those countries. And why is that? Absolutely a fascinating question. Today, 20th century medicine fails to think about prediction and prevention, and that is critical to 21st century medicine. And it's only 21st century medicine that can really fundamentally change the cost equation. And the way that they're going to do that is they're going to shift the focus of medicine from 98% on disease to 95% on wellness, and give it the proper kind of balance. And we'll talk about exactly how we do that. And finally, hospitals are really dangerous. You want to stay away from them. In the last 5 years, I've had 3 really good friends go in for utterly trivial operations and die from the drug-resistant bacteria. So I'm going to tell you that 21st century medicine is going to move the focus of medicine from hospitals to homes. So that's the take-home lesson. So when I went to Caltech in 1970 as a young assistant professor, I was really impressed with the enormous complexity of both biology and disease. And what I realized at the time is we had no good way to think about or discuss biological complexity, and later that came to be systems biology, and we'll talk a little bit about what that means. But what also happened about 1973 is I read a fascinating book that really changed my life, The Structure of Scientific Revolutions by Thomas Kuhn, who talked about paradigm changes in physics. And the points that he made were really interesting. Paradigm changes fundamentally alter how you practice and or think about a scientific discipline. They're hard to come by because you have to think out of the box, and most people have a real difficulty in thinking out of the box. But he said, even more important, once you've shown that your paradigm change is valid, it's hard to get it accepted because scientists tend to be very conservative and extremely reluctant to give up what they learned early in their careers. And I found that to be true really in spades. And I'm going to talk about 7 paradigm changes I've gone through, not the details, but I'm talking about them because each of them pointed a way toward dealing with biological complexity, and more important, each of them irrevocably pointed toward what 21st century medicine must be. So the first one you've heard a little bit about. We actually, over the years, developed 6 instruments that let you read and write proteins and DNA, and they gave us 2 really important things in dealing with complexity. For the first time, we introduced the idea that you could make very rapid measurements in biology, high-throughput biology. And what this did, of course, was, especially in the Genome Project, accumulate the data that was the beginning of big data and its analytics and so forth. One of these instruments, the automated sequencer, got me involved in the Human Genome Project, the second paradigm change. And that instrument was essential to sequencing the human genome. And what the human genome did for us were 2 things. One, for the first time, we knew every gene, and by inference, every protein, so we could begin to think in a global and holistic systems way about how to attack humans from this point of view of complexity and systems approaches. But the second thing it did, and it's really the most important thing in the near term for medicine, is it gave us access to human genetic variability and gave us the ability to correlate that variability either with well phenotypes or with disease phenotypes, and that turns out to be absolutely a critical component. The automated sequencer required bringing together engineering, chemistry, computer science, and molecular biology, and there I realized the idea that you ought to operate contemporary 21st century biology in the context of a cross-disciplinary environment with all sorts of scientists that learn to speak one another's language and learn to work together effectively in teams. And Bill Gates made it possible for me to go to the University of Washington and start the first such department. And that department, in the 8 years of its existence, was utterly spectacular in developing technologies that revolutionized genomics, proteomics, and other aspects of phenotype measurement. But it was in 2000 I realized that the University of Washington had enormous constraints for new kind of thinking. And they're the constraints that any organization generates through bureaucracy. And bureaucracies are honed by the past. They're just barely capable of dealing with the present. They find it almost impossible to deal with the future. And I think this is really true in industry, too. And you can say, well, we can do skunk works and we can do all these great things. The trouble with skunk works is they go off and begin their own new company. They almost never get integrated back into the original product. So how you create innovation in organizations is something I'm extremely interested in, but we haven't time to talk about that today. So systems biology took this global holistic view toward both biology and disease, and the next paradigm change over 4 years or so it did is it defined the parameters and boundaries of how we thought about medicine. So a systems approach to disease we called systems medicine, and we were convinced that healthcare really should circumscribe the 4 Ps: personalized, preventive, predictive, and participatory. And we'll talk about what all of those mean in some days, in some time in the lecture. Now, the next paradigm change was really one of the most interesting. We started asking ourselves, how could we bring P4 medicine to the healthcare system? And the essence of P4 medicine is that healthcare is really not just about disease, but about wellness as well. So in 2014, we designed a wellness project with 108 individuals where we did a 360-degree survey and created these enormously dense data clouds. And I'll tell you about the kind of data we generated in just a moment. But this gave us then the ability, when analyzed, to create actionable possibilities to improve wellness and or to avoid disease. And it attracted the attention of a healthcare system, Providence St. Joseph's, who came to me in 2016 and said, look, we'd like ISB to become our research arm and you are chief science officer. And after a debate, it seemed like an incredible opportunity to get into the healthcare system. Parenthetically, I'll tell you, I went to 6 top-flight medical schools in the preceding 6 years, including my alma mater, Hopkins, and made proposals that are only a fraction of what we're doing with Providence. And there I found how insular and siloed academic institutions are, where strong individuals have total veto power, even if lots of people like something. And so what was great about a community hospital is the egos didn't exist, and there's been nothing but enthusiasm. And we'll talk about just some of the kinds of things that we're going to be doing a little bit later on. So paradigm changes. What lessons did I learn? Well, almost every one of those were met with enormous resistance. And I'll tell you, when I was at Caltech, the first 2 paradigm changes I pushed, the biologists hated that idea because they thought it was unseemly to have engineering in biology. So they did, each of them, change the way we looked at biology in fundamental ways. And as Mark said, what was utterly critical in this journey was determined optimism. Because when you bring new ideas out, all the naysayers come out, and it's so much easier to be a naysayer than to bring something positive to things. So you have to be determined to make it happen. So systems biology has made a whole series of contributions to systems medicine, and I'm only going to talk about 3 really big ones. So one is this idea of personal dense dynamic data clouds, longitudinal data clouds, of many different types of data that, again, give us the opportunity to create actionable possibilities that let us deal and improve wellness or let us deal with and avoid disease. And of course, this is the essence of what precision medicine should be. And I'll tell you, precision medicine, as voiced by NIH, is a far cry from what we're going to be talking about here. Number 2, one of the really key points systems biology brought was the realization that in living organisms, we have a hierarchy of biological networks that extend from molecules to cells to organs to whole organisms that are seamlessly integrated and mediate the information that directs development, physiologic responses, aging, and if they become disease-perturbed, causes disease. And what's great about this way of viewing disease is if you can understand the difference between a normal network and its disease-perturbed counterpart, you get deep insights into mechanisms, into biomarkers, and into possible drug targets. And I'll show you later some examples of that. The other thing that we did very much from a systems point of view was to think about really important new kinds of technologies. And it's really unfortunate we don't have time to think about this, but we really pioneered together with others. We didn't do it completely ourselves. All sorts of new kinds of technologies, and I've added there digital measurements of self. But I'll tell you, I think the medical world has become over-enamored with digital measurements of self because in almost all cases, they are posse-dimensional in nature, and they only give you a fraction of what you need to know about the whole organism. They do add really important new kinds of information, no question about that. I'll tell you, third-generation sequencing is really going to be revolutionary. Nanopore-driven single-molecule sequencing, electronic detection. We're going to be able to read 500,000 base pairs and assemble easily your genome sequence directly rather than these short reads of 100 base pairs or so that we have to stitch together now. But what's even more revolutionary about these instruments is they will also be able to sequence RNA every bit as easily as DNA, and they're going to sequence proteins. And the reason that's important is with the nanopore detectors, we will have the sensitivity to be able to sequence proteins and look at all the modifications that come from covalent modification, from RNA editing, RNA splicing, all these kinds of things. And there's no good way to do that now. But even equally important, in DNA, there are 16 different chemical moieties that cause epigenetic modifications. We only know a lot about one of the 16. With these new instruments, we'll get all 16 automatically as you sequence the DNA. The second thing we really did was to use systems-driven strategies, and these are putting together one or more technologies in a computational platform that lets you do high-throughput biological measurements, and we'll talk about one or two of those. But again, what is really critical is those technologies and strategies open up completely new dimensions of patient data space that let us do things we never could do before. So in about 2014 or so, we saw the convergence of systems medicine, of these digital kind of measurements of big data and its analytics, and something I'll call connectivity. It's the internet and the internet that exists in living organisms, and I'm not going to get into that. But what this did was really emphasize the importance of the first P. Medicine has to be practiced at the level of the individual. It's really critical that we can tie together predictive abilities about what you're likely to run into in your life with preventive abilities to avoid letting you run into those difficulties. And finally, the participatory is the idea that the individual must participate in making decisions about their own health care, because in the end, some of the most important decisions you'll have to make are changes in lifestyle, and you have to do it. The doctor can tell you what to do, but we have coaches that have a spectacular new approach to that. We'll talk about that later on. I just want to show you how different P4 healthcare is from contemporary medicine. One, it's proactive. Two, it's focused on individuals. Three, it's all about wellness and disease, not just about disease. Four, it uses these personal dense dynamic data clouds, and what they give us uniquely the ability to do is to integrate your genetic information with the information you receive via your lifestyle and your environment. Those are the two major determinants of health, and genetics alone will only get you about 30% of what you need, so you need to do both of those things. And finally, I'm enormously skeptical about the classical ways that drug studies are carried out. So what do? We take 20,000 patients and you give them a drug or a placebo and you record the data. But then you ask yourself two really critical questions. One, are those patients genetically unique? And the answer is yes. And two, are those patients environmentally, lifestyle unique? And the answer again is yes. And we all know what happens if you average disparate objects. You enormously increase the noise over the signal. And pharma has spent billions of dollars demonstrating that that statement is absolutely true. So what exactly does P4 medicine suggest? We suggest that you have 20,000 patients, each with their unique data cloud, and that we interrogate those patients with regard to important questions like, for a given drug, who responds and who doesn't respond. And we can immediately segregate responders from non-responders. And because we have the data, we'll have the biomarkers instantly to distinguish those populations. And the reason this is really important is Genentech, with a breast cancer drug called Herceptin, had a really clever way to identify the 20% of the women that would respond to that drug. They took 46 women to the FDA with a 96% response. The FDA approved the drug. So if you stratify your population so that you get the responders to begin with, you save an enormous amount of money. And this is really important. These are the top 10 selling drugs in the US today. The orange person is the one that responds in each of the cases. The best case is 1 in 4. The worst case is 1 in 25. Imagine the dollars spent. Imagine the complexities that are generated by the fact patients respond incredibly poorly to drugs. And when you're done with a classic clinical trial in all these cases, you have no way to distinguish the responder from the non-responder. And that's the point that I've made. So as I said, P4 healthcare is about wellness on the one hand and about disease on the other hand. I'd say 96% or so of society's resources go into disease at this point in time. And wellness is viewed with a lot of skepticism, appropriately so, because there are quacks there. And that's why we've termed what we're doing as scientific or quantitative wellness. And what I think is going to happen over the next 10 to 15 year period is a whole new sector of healthcare will emerge, which is called scientific wellness. And my prediction is in that time period, the market cap of scientific wellness will come to far exceed that of a current disease and everything. So why is wellness so important? Here is absolutely a staggering statistic. You can do a calculation that shows 50% of the kids born in this calendar year are predicted to live to be 100. So the question I ask you is, what is the quality of their life for the last 20 or 30 years? And without wellness, it's going to be just what it is today. So that is really key. So in 2014, we set out this pilot project of 108 people, friends of mine in Seattle, who basically, Seattle and other places, right, Larry? Who basically agreed to go through a year-long query by dense dynamic personalized data clouds, and it was an IRB-approved study. And a really important point that has been published in several different papers now is if you ask about determinants of health, genetics is 30%, the environment is 60%, healthcare is 10%. So the really important point is we need the dense dynamic data clouds to be able to measure those two components that make up 90% of your healthcare, and that's these personal dense dynamic data clouds. So we gather complete genome sequence. We take blood studies every 3 months to measure clinical chemistries, metabolites, and proteins. We do the gut microbiome every 3 months. And then we do quantized self-measurements of various types used to Fitbit in these studies. And that generates billions of data points, which, again, if analyzed, lead to actionable possibilities that let you optimize wellness and or avoid disease. And as we've, over the past 4 years, gathered more and more data on individuals, we've increased enormously the list of actionable possibilities. And as we've integrated different data types, we've made them far more subtle and more targeted in precisely going to individuals that will get the maximum benefit out of them. So what we actually did was every month we reported back to the individuals that a few of their actionable possibilities, never giving them too many. And we'll talk about how many is too many in just a moment. And we did it with what we called scientific wellness coaches. So these are people trained both in biology and in psychology who could go to the individuals and explain what the actionable possibility was in simple terms. But because they had previously interviewed each subject with regard to what their real health objectives are, and that's an incredibly interesting question to think about. Most people struggle for a half hour or 45 minutes before you finally clarify what you think these are. But they were able to put then each actionable possibility in the context of the individual's own health objectives. And by doing this, we had more than a 70% compliance. So health coaches are really going to be important in the future. Doctors absolutely do not have time, nor frankly, in most cases, do they have the understanding to do what the health coaches can do. We bring them in and train them actually for 6 weeks, very intensely on all the things that they have to know. And they're really spectacular. So a key thing about the coaches is they become your mother, and you want to please them. And they're the key to longevity because they are the person who persuades people to re-up and continue this whole process. And to prove to them that it's really beneficial to the individual, not as a one-time thing, but as a long-term objective. So I've hundreds of stories I could tell you, but I think one of the most telling is on the first set of blood studies we did, 91% of the individuals had nutritional abnormalities, 68% inflammation, and that was mostly related to diet. And we had reasonable number with cardiovascular and diabetic complications. In fact, 53 individuals were pre-diabetic, and determined during the course of the year, we moved 8 completely to normal and almost the entire set over much closer to normal. And now that we've continued with some of them, many have moved completely over to normal. And we could deal very effectively with the nutritional limitations. Many of the nutritional limitations come from defects in your genes that relate to metabolism. So you really need supplements to make up those kinds of differences. But I think the bottom line was the pioneers were enormously enthusiastic, and I think almost universally felt that they really had gained fundamental insights. And one thing they loved was the fact, with knowledge, they could make their own healthcare decisions. And I think that's really a critical part of 21st century medicine. If individuals have the knowledge to make their own decisions, we're going to save lots and lots of dollars for a variety of different reasons. They came to understand that your genetics weren't your destiny. They just defined your potential, and on most cases, there are ways you can circumvent at least many of the genetic limitations, not all. But I think the most important insight was the realization on the part of almost all of them is they weren't nearly as well as they thought, at least in terms of all the different actionable possibilities that came up for them. And in fact, what's interesting, I would argue if you had this ladder of increasing wellness, that the average person would be pretty far down in the ladder. And of course, the actionable possibilities move you up step by step. And what we would really aspire to do over time is to move you up to a point that we match Eric Topol's Welterly. So these are people that are 80 or 90. never been sick a day in their life, never had a drug, never been in a hospital, and they go into their 90s mentally alert, physically capable. So if we can move people up to the elderly, then we could guarantee that. Now, of course, the real question is, how long does the guarantee hold? And what is really interesting about aging is when you move into the hundreds, most people die by very rapid complete systems failure. So you save money for your family, you don't go through all. So we aspire to get you to be 100, and then you're on your own. You'll have to deal with it yourself. And what I'd argue is scientific wellness should be a lifetime objective. We started in mid-2015 a company called Airvale that brought to the consumer scientific wellness. And I'll just say that the company now has about 4,000 consumers, and some of them have been with us for 4 years now. So we have enormously valuable longitudinal data, and you'll see in a few moments just how valuable those data are. So these personal data clouds, I think, are really akin to the Hubble telescope. It had the ability to look into the universe with a resolution heretofore unachievable and defined all sorts of fascinating new possibilities. And with these dense dynamic data clouds, we can look at human biology and disease with a resolution heretofore unachievable. And we recently published in Nature Biotechnology, it's not in press, it came out in August, a paper on the analysis of data from the 108 individuals. And we saw that there were three kinds of conclusions that were really striking. One, we could do beautiful statistical correlations, and that opens up completely new approaches to drug discovery. Two, we demonstrated that we can predict for each of you your genetic risk for more than 60 diseases, and that opens up entirely new ways to think about prevention. And three, we were able to see beautifully wellness to disease and disease to wellness transitions. And those are key to being able to handle either or both of those kind of things. So the statistical correlations, we had 6 major different data types, and we asked of a data bit within a data type to compare it against all other data bits and the 5 other data types and ask if there were statistical correlations that we could ascertain. And when we did that, we had about 3,500 statistical correlations, and we corrected for multiple hypothesis testing and all of that. I mean, in a sense, we can argue about, with such a small number, how relevant are these things. But it's irrelevant because with 4,000 people, we're seeing exactly the same things, only in much more detail at much, much higher resolution. But what you can do is you can take those correlations and they beautifully generate this big hairball that doesn't tell you anything about anything. And operationally, what we did computationally, and this isn't quite how we did it, but it's close, is we essentially cut all of the edges in this hairball that had the lowest probabilities. And in doing so, what we did was to generate discrete communities that turned out to correlate beautifully with physiology, with disease, with biomarkers, with all sorts of things. And what you could do is go to one of these communities, say the cholesterol community, and you could see all sorts of new compounds that might really be intriguing drug candidates and or biomarkers in various ways. So the data let us come to correlations, but what is really important is once you have the correlations, they let you generate hypotheses. But what is critical in healthcare big data is you have to insert domain expertise so you can formulate relevant hypotheses. And I'll argue engineers are not sufficient in their domain expertise in biology. They're great in what they do. Once you've formulated the hypotheses, then you can do perturbation experiments. And we've done that for a couple of examples. And they reveal beautifully insights into disease mechanisms, new kinds of biomarkers, and new possible drug target candidates. And then you can go back and to the big data and get more and go through this entire repetitive process. But the correlations alone are just the beginning of the process. And you need to be able to marry the beautiful, powerful techniques of computer science with the beautiful understanding of biological models and so forth. We can determine your genetic risk for at least 60 diseases, and we can do so because there are a whole series of studies, 60 different diseases, that have been done that are called genome-wide association studies. And in some cases, thousands of markers have been identified. In each case, they represent a very low probability explanation of that disease. But because we know the complete genome sequence, we can actually sum up both the positive and negative possibilities. And then what we did was to take 2,000 normal individuals for a given disease risk and generate what's more or less a bell-shaped curve. And of course, you could either, if you're on the right-hand side, you have a very high probability of risk for that disease. If you're on the left, a very low probability. And of course, you can go through a whole series of diseases. Ldl cholesterol, you might be high. If you wanted to look at diabetes, maybe you'd be much lower than that. If you wanted to look at Alzheimer's, you might be low. And breast cancer, you might be intermediate. But the really important thing is there are more than 60 different diseases that we can do this for. And we can certainly take easily the major chronic diseases, and I put Alzheimer's in that category, and we can estimate those that are in the upper 10% genetic risk for Alzheimer's, and there are special things you can do with them, and we'll talk about that just a little bit later. But what we did for LDL cholesterol, and this is really an important point, is we binned the 108 individuals from low genetic risk to high genetic risk. And then what we did was to take those individuals and look at all of the analytes that we'd analyzed in our studies. And we were able to show beautifully that the LDL cholesterol level correlated perfectly in a linear way with increasing genetic risk for LDL cholesterol. Now, the really important point is none of these people have heart disease or any kind of disease at all. What the cholesterol is a reflection of is genetic risk. So the really interesting question is, could we take these very high-risk people and lower the level of cholesterol and convert them from a high risk to a much lower risk? And the answer is absolutely. Let me just say there were other analytes and proteins that correlated too, and they all raised really interesting new possibilities. But I had a friend that had three generations of his fathers die of heart attacks by the time they were 60 years of old or younger. And he was incredibly compulsive about his LDL level, and it was great up until about 35, and then it just went exponential. And he found at the same time, without changing his diet, he gained an enormous amount of weight. And of course, what he did was start taking appropriate statin. It brought his level back down to not quite as low, but very low. And he's now 65, and he's perfectly normal. So that is an example of where a high genetic risk had a reflection that you could use to manipulate the genetic risk. And I'll tell you a really interesting one that we're intrigued by is with inflammatory bowel disease, where we've been able to, again, plot out, now we're talking about 2,000 individuals or more, the increasing genetic risk toward the right, and we show beautifully that the level of cysteine really declines in a striking fashion. So a really intriguing question is, if we increased in these people, none of whom have inflammatory bowel disease at this point in time, the cysteine level, could we move them off that very high risk level? And we haven't done that experiment. But what is interesting about cysteine is it's a key part of a mechanism that creates a compound that is an antioxidant that is really important in suppressing inflammatory bowel disease. So when cysteine level gets low, you lose that oxidant, you increase the probability. So it makes sense, but we haven't really tested this. Transition states, and I'm just going to show you one really spectacular one. We had a woman in the study for about 3 years, this past January diagnosed as stage 4 prostate cancer, which is really a grim diagnosis. We had 4 bloods that had been drawn prior to that time. So what we did was to take, at the time we did this analysis, all 2,000 individuals we had, and we looked separately at each of the hundreds of analytes we'd measured to ask whether she had analytes that were outliers, way beyond what the normal people had. And what's interesting is with all 4 of her bloods, we showed that there was one protein analyte that was way beyond anything anybody else had. And it turns out that that protein is expressed specifically in beta cells of the pancreas, and it's a key differentiation molecule. So it's such a logical candidate. Now, this is a correlation. It isn't formal proof. But, you know, it really raises a very interesting question. We have now the ability for each of you to ask, for any given disease transition, do you have any outliers? And I think one of the really interesting questions is, I'll bet with individuals, there are going to be a subset of outliers that are unique to you and a subset that will be shared with other kinds of people. And that collectively, those outliers will explain in fundamental ways aspects of the disease mechanism. And we've now seen probably transitions for all of the common chronic diseases, and we're beginning to look at those in exactly the same way here. So what we're excited about is, as we move to the end of this year, we'll have 4,000 or more patients, and we'll be able to look at these very earliest disease transitions. We'll be able to use the data clouds to get biomarkers that will mark the earliest transition, and then some of these systems technologies we didn't really talk about to go after targets for therapeutic reversal of approach. And of course, if we can do that, then this is going to be the preventive medicine of the 21st century. And my argument is, if we can do it for all common chronic diseases, there will be a time when we'll be able to assure any individual they'll never get any one of those chronic diseases for which we can do. How long is that going to take? It really depends on funding and things like that, but it's already underway. And what's important is the paradigm change is now realized, and many other people will begin adopting these ideas. So we're all interested in aging. So how do we use these studies to talk about aging? So an analysis we did was to look, in this case, at metabolites, and we binned about 3,000 individuals into 10-year decades, going 20 to 30 all the way up to 80 to 90. And what we found as you got increasingly older, the variability in your analyte expression went up in a linear sort of way. So as you get older, you have less control about specification of metabolites. We found exactly the same to be true with clinical chemistries and exactly the same to be true with the proteins that we measured. So what's really interesting is we can now think about biological age vs chronological age. So, for example, suppose that you look at that decade there. There will be individuals in that decade that are at the very low end of the range, which is about the same range that the typical person in the 20 to 30 category is in. So you might argue that person's biological age is 20 to 30, whereas their chronological age is 60 to 70, or whatever it is. And exactly the same is true at the other end. There are people that appear to be much older than they are, and they're off the scale there. But the point is, we can, for each of you, then generate biological ages, and the ratio of those ages will give you a sense of how well you are. And there are other ways we can do this, too. So, as I said, Providence approached me in 2016 to become Chief Science Officer and make ISB their research arm. And we agreed to do that. Providence serves 7 states, has 50 hospitals, sees 5 million patients a year. It's a $20 billion operation. It has 30 million electronic medical records, incredible data we'll be able to look at and so forth. So what exactly are we thinking about doing? We've established a Center for Translational Systems Medicine at ISB that has 4 major objectives. Actually, it has about 8, but I'm only going to talk about 4. So one are something we call translational pillars. These are clinical studies. I'll define those. The second, we're creating the technology platform that for the whole system will be able to do the dense data clouds very rapidly and very inexpensively. Third, we're setting up a model clinic in one of the hospitals in the Providence system for wellness. And we're going to bring in many dimensions people have never thought about wellness before. And then finally, we're thinking about how to educate physicians and other healthcare professionals in the system as to P4 medicine and scientific wellness. So what about the translational pillars? There are 9 of them. We're starting clinical trials as we speak on the first 2, scientific wellness and Alzheimer's. So we're taking 1,000 Providence employees for 3 years, and we're going to evaluate then how much their health is improved as contrasted with a random 1,000 employees from Providence that don't go through the program. And we expect to be able to show enormous savings, and I'd be glad to talk about that in as much detail. But just think, Alzheimer's costs us $260 billion a year. 5 million people have it. Both those numbers are escalating rapidly. Suppose I said to you, which I really believe, in 5 to 10 years, we'll be able to reverse Alzheimer's before it ever manifests itself as the disease phenotype. And that's the second test we're doing now with 2 outstanding Alzheimer's investigators using these dense dynamic data clouds and a series of relevant technologies. So these will be clinical trials like no clinical trials ever done before. The future of healthcare. We've brought P4 medicine and scientific wellness to the healthcare system. We're using precision medicine in the sense of the personal dense data clouds that allow you again to assess environment and genetics. Really a critical kind of point. We can quantize wellness, optimize wellness through data-driven, actionable possibilities. We're going to be able to get the earliest disease transitions and make this the preventive medicine of the 21st century. Healthcare costs, we think, will really come down dramatically. Scientific wellness should be a lifetime journey, and we think there's going to be a whole new sector of the scientific wellness industry. I think the data that I showed you are going to transform how most major industries in the healthcare arena think about biomarkers, drug targets, and even biological mechanisms. And the one limitation for scientific wellness now is the cost of the assays. And they're coming down by a Moore's law. So in 5 to 10 years, they'll be 10% of what they are now. And what excites me about that is we can really think about bringing scientific wellness to the developing nations of the world and to a democratization of 21st century healthcare that would have been inconceivable before. So, a few last points about P4 healthcare for wellness and disease. You understand how important personalized is because that lets us optimize wellness and avoid disease through the actionable possibilities we discussed. And it lets us, in a sense, take 20,000 individuals where each is an N of 1 clinical trial, and we can investigate from the N of 1 clinical trial the deconvolution of enormous complexity, but we can segregate and aggregate and learn general properties as well, so you can go in either direction. The predictive, the ability to predict genetic risk for most of the common diseases is going to open up the possibility of putting a big red star by you so we watch you very closely in the future. And of course, the preventive is the wellness to disease reversal of transitions. It's taking this genetic risk and again, determining whether these analytes that correlate with genetic risk can themselves be used appropriately to mitigate genetic risk. And I'll almost guarantee you that's going to work. And then optimizing wellness, and that will certainly facilitate avoiding disease. And the participatory part is actively responding to the coaching and to changing their lifestyles in an appropriate fashion. And I think having people informed and making their own decisions is really going to save the healthcare system lots and lots of money. The outcomes and expenses for the current healthcare system are grim. So we spend $10,000 per year per patient, infinitely more than any other nation in the world. Economists estimate that this cost is going to grow at 5.8% per year up to 2025, far greater than GDP and all of those other things. And remember, 86% of the healthcare costs are spent on chronic diseases. Suppose we can eliminate most of those. What an enormous kind of saving. And the outcomes. 1 in 4 is harmed in the hospital. 12 million serious misdiagnoses a year, and on and on. I mean, outcomes that are really, really grim. So what I would argue is 21st century medicine, which is what we've talked about, has really 2 essential features. One, wellness has to become a major part of the healthcare system, and that's going to be a lifelong journey. And 2, wellness to disease transitions are the key to eliminating chronic disease and saving lots of dollars. And of course, all of this is going to get us to the point where we'll be able to do all of the things that we've talked about. First, so to move them from the dangerous hospital, first to doctors' clinics, and then finally to the patient's home. And I predict in 10 years we'll have a tricorder. You can press your thumb, it'll take a drop of blood, it'll make 6,000 measurements, it'll give us all the things and more that I've talked about here, and it'll all be done in the context of absolutely routine, on your way kind of. So let me say, with 20th century medicine, there's nothing you can do to it to move any of these parameters away. You can optimize little bits and pieces, but you need to fundamentally rethink what healthcare is. Thank you. Okay. if you don't clap long, we have time for some questions. Yes?
Dr. Hood, what prevents the big pharma industry from keeping you from doing this? You just talked about how we'll lower our costs dramatically, but in doing that, you've just reduced the income to all those companies that are really out there for the purpose of making money for their stockholders. How do we prevent that from happening?
Well, that's a good question. What I would argue is, and what we're trying to do now, is say that all clinical trials should be a two-step process. We should take 20 or so patients and do a quick trial on your drug and do it with this NF1 kind of study. And what we can learn from 20 is, one, are there off-target hits? We'll see that clearly. And we'll see it because of all the data we have on all the different organs and everything. Number two, we'll be able to stratify the disease into major subtypes. And number three, we'll be able to stratify patients as to those that respond or don't respond. Then you can take those markers and get a population, and what I would argue to them, get 40 people who are responders, take that to the FDA and get your drug approved for a fraction of the 1.5 billion typical pharma company now spends on these kind of things. The other thing is a lot of the earlier stage studies are really complex, and these dense data clouds give you a view of a lot of the biology that would really facilitate the preclinical kind of studies. So that's one aspect to it. And I think the second aspect is really a tough one. And we've been through this with pharma. You know, at one time, pharma thought erythropoietin was the ideal model of a drug that was blockbuster. It lets you do a gazillion different things. My own view is, as we get into chronic diseases, there's going to be no chronic disease for which a single drug will operate. And I would say they're going to be very much like AIDS. You'll need 3 drugs or more, so you need to think about ways that you can assess the combinatorics of a lot of different drug possibilities. And again, systems approaches give you powerful ways for doing this. But the real problem with pharma is the young people see the power of this. The people who make the decisions are really bound by the past. And so you've got to have somebody who breaks loose and is willing to try this to show how well it's going to work before most are going to come. I think it's this paradigm change and the conservatism of the pharma system. I remember when I argued till I was blue in the face that proteins could be great drugs, and they said, oh no, only small molecules, proteins will never work. Most of the best drugs are proteins today. And so you just have to go through these things in an agonizing sort of fashion. And it's really unfortunate because we could really change things rapidly, but you have to convert the people who make the decisions, and they're the hardest ones to convert. Yes. Pardon? Oh, yes. There's a mic.
We're trying to share sides of the room as well.
Okay.
Roger Payne, how do we join your studies? Is it through Aravail?
Yeah, that would be the best way to do it. In another year, we'll have a clinic, if you live anywhere in the Northwest, at Swedish Hospital that'll be super and do many things. But right now, joining Aravail is the way to do it. And so. Right.
Did you all hear me? I said
Yes,
we didn't
I
talk
did.
about.
That is utterly a great point. I think mental health is really critical, and we're thinking about ways to be able to deal with this really effectively in large populations. So we're starting to bring on people that have the expertise. But the other thing I'm really intrigued by there is a company called Prosit that has come out of UCSF by a National Academy member, Kevlis Prize winner. I mean, really classy scientist. And what they can do is give you computerized tests that quantitate cognition in really interesting ways. So for example, on the Alzheimer's test, we're going to integrate that right in so we can follow cognition and reversal and all of those kind of things. So I think there are two different things you can do with the mental side of things. One is optimizing cognition, and that's just like optimizing health. But the other is dealing with mental disease and things like that. It's important, we just haven't done it. So why don't you give speakers and they can ask.
Lee, thank you very much for a really eye-opening talk. I'm Hank Wu, also went to Hopkins for medical school. It's wonderful to see you. 3 quick questions. What is the optimal ratio between your guidance counselors and number of patients?
Boy, that is a terrific question. The best counselors easily can handle 100, and they're probably easily going to be able to handle 150. That is the part that doesn't scale as well. So right now, Airvale with 4,000 people has 70 counselors. It's the biggest population in the company, but it is the really unique secret sauce that makes the company work. And what I'm trying to do is persuade nursing schools to take scientific wellness as a new major, and it would be terrific if we could move some people in that direction.
Do I have to live in a certain place to join Airvale, or is it
No,
boundaries,
it's
no
national
physical?
now. It's national.
So it's fairly
So
virtual.
if you just go on the website, they'll explain everything. But no, if you want to get on, you can do it from any place except, I think, New York. They have really horrible rules and we're just not done with all the due diligence. But I think every other state we're in.
Last question. You mentioned 70% compliance of
Yeah.
the 108 patients. How is compliance defined in that case?
It's defined by carrying out the suggested actionable possibility. So we kept track for each person of how many possibilities they were given. And then you can assess most of them that they have. The actionable possibilities often are reflected in quantitative changes in the measurements we make. So it's just like smoking. We had 100% of the people say, oh, we don't smoke, but there were 2 people that did smoke, and when we approached them and said, look, you can't have this compound unless you smoke, they said yes. So you can't lie to your metabolites. Yeah. He's got a microphone.
Okay. Yeah, so the idea of having certain patterns of health and then having preventative interventions is pretty incredible. But I was wondering if this data slips out, whether or not it can systemically affect people, when it comes to insurance or employment opportunities once this becomes like a major systemic thing.
Well, the insurance is really a critical issue, and that's why we're doing the clinical trial on wellness at Providence with 100 going through the Airvale program and 100 controls. And I think there we can prove both economics and the validity of improved health. And those will be the dual requirements for payers to move in this direction.
Okay, that's fair.
So I would like to, we have folks who come to us from Europe and far away, and we get them to bed.
Okay, okay.
But I'd like to mention something about Lee's being with us this evening. In addition to giving a great talk, thank you, sir,